Good morning, all of you. My screen is visible. Hello? Anybody? Hello? Hello?
Yes, sir.
Screen is visible, ma?
Yes, sir.
Okay. See, previous class we observed VA characteristics of SCR. Now we'll see some small logical problems. Whether the device is turned on or not, what is the pulse width, all these things based on the latching current and holding current. As I mentioned you in the characteristics case, latching current is a minimum anode current is required to maintain in the on. If the current, anode current is not reaches to latching current, then what will happen? Device going to be turned off. That is one thing. And holding current means if the current is below which device is going to be turned off. Now the problem is latching current of the circuit is given 4 milliamperes. Let it be this is the circuit. Latching current is mentioned. Obtain the minimum width of the gate pulse required to properly turn on the SCR. Then the question is, we need to provide as a firing pulse to turn on the SCR. So they are asking width of the gate pulse. So if this width is less than some value, means ensure that width of the gate pulse, if you provide such a way that during that time the thyristor anode current must reaches to the 4 milliamperes. Otherwise what will happen, automatically device is going to be turn off. So that is the reason. So how much width we need to provide to reach anode current is equal to the 4 milliamperes. So for that, you know the inductor formula, voltage across the inductor, L di by dt. From this dt is equal to L by V into di, and apply integration, then what will happen? T is equal to L by V into I. Now if you provide T this much, then the device is going to be continue to on. The reason is, what will happen? We consider that current I, so that is this much. So we required this much current, so we consider here. Therefore, to get that much current, we require this much time duration. So you just substitute that L value and V value. So L is 0.1, V is 100, and I is 4 milliamperes. So 4 into 10 power minus 3. That will get 4 microseconds of time you need to give the gate pulse. So this is the one problem. If you keep that width is 4 microseconds, then only the device will continue to on. That's what minimum width of the gate pulse is required to properly turn on the SCR. That will be as a 4 microseconds of time. Now one more problem we see here. This one. So now there is another problem. We can see that latching current of a thyristor is 50 milliamperes. So IL is given. Then the duration of the firing pulse is 50 microseconds. Whether thyristor will get fired or not. What is the difference between previous problem and this problem? Previously IL is given. Something current is given. They asked what is the width to maintain in the arm. We calculated T. But in this case, latching current is given and width also given. What we need to find is whether the thyristor will on or not. What is the condition? If you give this much duration, you must find what is the current. What is the anode current you find. If this current means anode current is greater than latching current. What is the latching current here? 50 milliamperes of current. So under this condition, then only thyristor is going to be fired. Otherwise, it will be turn off. The question is whether the thyristor gets fired or not means simply find the current pass through the circuit. If that current is greater than 50 milliamperes, then it will fire, otherwise turn off. So for that RL circuit excited by the voltage, then I is equal to V by R into 1 minus e power minus t by tau. This is the formula, R minus R by L into t. Now tau is L by R. We calculated that L is known, R is known, and simply voltage is given 100 and R value is 20. 1 minus e power minus t by this. So if we substitute like this, you will get it. Here t is also given. The problem t is given. Firing pulse is 50 microseconds. So you can substitute 50 microseconds there. You will get current. So once if you substitute the 50 microsecond, what is the current? 9.99 milliamperes. From this we can easily statement we can give whether the thyristor is on or not, or fired or not. Then what is the current we required to maintain in the on? 50 milliamperes. That is the latching current. But how much? If you give width is only 50 microsecond, current is only 9.99. Then to maintain on, we require to give more time firing pulses. Then only current will increase further. But at moment they already mentioned 50 microsecond. So that time is not sufficient to reach thyristor current or anode current to latching current. That's why thyristor is going to be turn off. So that is only the reason. Here you can see there is a value of current is less than that. That's why it will not fire. So that is the thing we can see in the case of so now we'll go for the next one, turn on methods of SCR. So this is one of the important topic. We required to give the gate bar to break the junction J2 only thyristor is going to be fired. So we have some of the turn on methods. So we'll see one by one. Already we noticed two things. One is the forward voltage triggering, another one is the gate triggering and all. By changing the gate current, we can able to turn on the thyristor below the breakover voltage. In this turn on methods of SCR, you can see that with the anode positive with respect to cathode, thyristor can turn on by any one of the following method. We have 5 methods. So one is a forward voltage triggering. This is the method we noticed in the characteristics itself. Anyhow, I will explain once again. That is a forward voltage triggering. Second method is a temperature triggering. And third one is a light triggering. Temperature or a thermal triggering, both are same, and light triggering. And next one is a dB by dt triggering, and then gate triggering. So these are the methods we have to turn on the SCR. Then SCR includes 2 states. What are that? Namely forward conduction and forward blacking mode. So forward blacking mode I call it as a off state. Forward conduction mode I call it as a on state. So SCR is switching in forward blacking state to forward conduction state, which means what? Off state to on state. So that we call it as a turn on SCR or turn on methods of a SCR or triggering methods of a SCR. This is only we have 5, but actually all the methods are not suitable to fire the devices in general, but it will fire. But thing is, we don't use. Some of the methods are unwanted methods. We'll see one by one. Now first one is a forward voltage triggering. What is the forward voltage triggering? As you know, the thyristor diagram, 4 layers, PN, PN. Now we are connecting anode to cathode, some voltage, let it be as a V. And then what will happen? You can see that if we give supply to that thyristor, then what are the junctions are forward bias? Plus is connected to anode, minus is connected to the cathode. Then J1 and J3 are forward bias. only junction J2 is a reverse bias. So it won't allow any current pass through the device because of the junction J2 is a reverse bias, except very small leakage current. That leakage current is very small, therefore it is insufficient to break the junction J2. That's why you just open the gate as such and you try to increase anode to cathode voltage. Now we are increasing this voltage. Once if you increase anode to cathode voltage, then what will happen? You can see at this point, width of the depletion layer will be decreases because voltage is inversely proportional to the width of the depletion layer. So that is the reason width will be gradually decreases. Finally, that is going to be breaks down. When it will be breaks down, if this voltage increases up to the VBO, VBO is a forward breakover voltage. If you increase that much voltage, then junction J2 will be breaks down. So due to this transient, initially it is off state, but we are keep on increasing the voltage. Suddenly junction J2 going to be breaks down. Immediately there is a chance at that moment the voltage across from anode to cathode may be beyond breakover voltage. That leads as a problem to turn on the device. You should not allow the voltage across anode to cathode beyond the breakover voltage. That is the problem. That's why generally this forward voltage triggering method will not be preferred. But there is a chance or there is a provision to trigger the SCR. So that is the reason we can use this type of a triggering method. See the temperature triggering. Second one is a temperature triggering. So what is the temperature triggering? Here we can notice that same as in the previous method, forward voltage triggering method. I said junction J2 is a reverse bias, but very small leakage current pass through the junction J2. That leakage current will leads, what will happen? Temperature will rise. Leakage is nothing but a power dissipation there. No, because of that leakage current, there is a temperature will rise in the junction J2. But once temperature is rise, again there is a resistance. Junction resistance is going to be dropped down. If the junction resistance is dropped down, again leakage current will increases. With this process, so cumulative process, leakage current will increase, the temperature will be dropped down, again leakage current will increase, like that. With the cumulative process, some point of time, the junction temperature will increase beyond the specified value. Then automatically junction J2 is going to be breaks down. But this method will not be preferable one. This is an unwanted triggering. Why I call it as unwanted triggering? In general, whenever you want to fire the device, at that instant only device has to fire. Rest of the instants like temperature increasing, these are all internal process. Whenever if you give anode to cathode voltage, normally small leakage current will be there. Because of that leakage current, it is going to be triggering, but it is not in our hand when it has to trigger. That's why this method is not a intentional method. This is what automatically it is our unwanted triggering is going to be happen. You need to prevent this method. Otherwise, what will happen? Automatically, whenever the temperature will rise, it is going to be turn on. So for that reason, we can say that to prevent temperature triggering, we need to use heat sinks. So the device has to be mounted on the heat sink. Then whenever temperature rises, it is going to be a heat sink purposes, it will absorb the temperature. So it is always observing the temperature so that it will maintain within the limits. So once the temperature is within the limits, it will not be trigger. So that is the unwanted triggering, but it will happen if you not take care of that. So that's why to prevent temperature triggering, we need to use heat sinks. That's what I mentioned the theory part, all these things here. Now, light triggering. So now we can see here there is a beam or electron light fall, or you can say that laser beam thrown onto the junction J2. So this is all very accurate method, or very sharp triggering. So it generates what will happen if we pass the laser beam onto the junction J2. There is electron hole pair is going to be increases. So then what will happen? It generated minority carriers across the junction J2, and automatically it reaches to the P2. That is a P1, N1, P2, N2. That is gate is near to the P2. Then we are thrown the laser beam onto the P2. Then electron hole pair will be increases. Due to this, what will happen? High electric field, minority carriers are accelerate and strike on the covalent bond, and further there is electron hole pair is going to be increases. If again electron hole pair increases, high electric field strength will be caused, and consequently more and more electron hole pair will be reaches at the junction J2. Then the junction J2 is going to be breaks down. So that will be used very sharp time and high accurate turn on process. We can use that. That will be in the HVDC transmission. That is a lasers will be used in a HVDC transmission. Under that devices to turn on, we use the light triggering methods. And another one is a dV by dt triggering. This also has an unwanted triggering. So why we call it as unwanted triggering? We can see that why the dV by dt triggering is going to be happen. Now, initially the device is in off state. Let us assume that switch is in the open. At any point of time, there is a switch. Something is connected across the source. So now we can see this whenever supply is given. Then what will happen when the supply is given to here without closing the switch? I am telling the switch is open. And when the supply is given to this point, what is the voltage across the switch? Normally, as you know that in the previous case, voltage across the switch is same as the source voltage. But suddenly, or otherwise also any device is there, you can connect the switch and you can connect the supply, whatever, anything. It may be thyristor and then something load, and we can give as a some supply. Then if supply is given, switch is closed here, the rate of change of voltage across the device is going to be very high, the moment. But now there is a specification for the device. Rate of change of voltage should not increase beyond the specified value. The dV by dt value they will give. Once if you know the dV by dt value, once the switch is closed or supply is given, immediately the moment rate of change of voltage will increase beyond the specified value, then automatically junction J2 is going to break down, it will be triggered. I will show that small derivation also in that. Now, the rate of rise of anode to cathode voltage is high. Then what will happen? There is a charging current through the capacitive junction is high enough to turn on the thyristor, because there is a specified limit for particular thyristor. All the thyristor may not be the same for the dV by dt. Depends upon the rating of the SCR, we may have the value of dV by dt. If the rate of change of voltage beyond that specified value, automatically device is going to be triggered. That's what charging current may destroy the thyristor, and the device must be protected against dV by dt. So how we will protect that? And now this is the normal formula current, capacitor current. There is a, or you can say that once the device switch is closed, the rate of change of voltage we can represent like this. there is a IC is equal to dq by dt, q is equal to cv, then apply UV rule, then we can get it. This is the relation. From this, what will happen? dc by dt, capacitance will be the constant. That means across that device. And now what will happen? The C into dV by dt, C also constant. What is C here? Junction capacitance. Because why I call it as a junction capacitance? All other layers are turn on, means forward bias. Only junction J2 is a reverse bias. And then this side will be positive charges will be there, this side negative charges will be there. Now that will be act as a capacitance. So that is a junction capacitance. We can see that this will be fixed one, and I see that we can see that directly proportional to the dV by dt. So whenever dV by dt increases, automatically current passing through that device or leakage current, or you can say that is also going to be increases. So once if dV by dt is more and more, automatically current will be more and junction J2 is going to be breaks down. And this is the phenomena. We'll get it as a dV by dt triggering. And now we can see that why that will be as unwanted. So whenever switch is closed, because of that only rate of change of voltage will rise and it is going to trigger. But that is also unwanted, because we don't want to fire the device the instant at which supply is given to the device. When it has to be fired, whenever you want to fire, that is all about your control or your requirement. At 0 degrees I want to fire, or 30 degrees or 60 degrees or something like that. Depends upon your requirement, you need to give the firing pulses to that particular device. Then the device is going to be fired. And now we can see that gate trigger. And how to overcome this drawback? You can see that because of that only the device is going to be triggered. That's the reason what I will do is, if I connect one capacitor across this yet moment, not finally, yet moment, if I connect one capacitor across that, if I close the switch, then what will happen? If I close the switch here, then the rate of change of voltage is 0 initially. The reason is capacitor will act as a short circuit. The moment the switch is closed, then the rate of change of voltage across the device is 0. When that is 0, there is no meaning of dV by dt high value. So that's the reason we can able to fire the device. So that is the reason the device will be fired if capacitor is not there. And now when there is a capacitor and the switch is closed, immediately the voltage across that will be 0, and gradually this capacitor is going to be charged. Once capacitor is going to be charged, then what will happen? The voltage across that capacitor is same as that of the voltage across the device. So it won't be happen any rate of change of voltage is high. So that is way, or this we call it as a snubber circuit. Not only one, this one actually, there is a, while it is, once you want to fire the device at any instant, let it be if the capacitor is sufficient to prevent the dV by dt, no doubt in that. But there is a problem while it is firing the device. Now we can see that capacitor is used to prevent the dV by dt at moment. But now after some time I want to fire the, I am audible? Hello? Anybody? Hello?
Yes, sir.
Yes, sir.
Okay, fine. And now whenever I want to fire the device or I want to trigger the device, this is used to prevent the dV by dt. But now after some time I want to fire the device at an angle of 30 or something. Then if I give the firing pulses, then what will happen? This device will fire, means it will conduct. Once if it is conduct, then what will happen? Because this is already charged now during off state. Switch is closed, capacitor is charged. Initially 0 and then gradually it is charged. It will be getting some voltage, whatever the source voltage or something. While the thyristor is closed, then what will happen? Capacitor nature is what it is going to be discharged. Then current is passing through this way. And whenever current is passed through the thyristor, then how much current it will pass? There is a load current as usual, it is passed to the load current. In addition to that, what is the value of current here passing through the thyristor? Current I is equal to V by R. V by R. What is R? Internal resistance of this capacitance, let it be. That value is very small. Let it be 1 ohm, let us assume that. Then what will happen? Current I is equal to V. What is the V? 230 volts. Let us assume just voltage is 230. Then I is equal to V. Then what will happen? This V means that much current is passing through the thyristor unwantedly, because we read only load current. So if you pass that current is very high, then automatically the current is very high. So device has to be used, high rating device. To prevent that, what we have to use, we can use as a resistor in series with the capacitor, external resistor. Then what will happen while it's discharging? It has to be act, means high resistance, normal junction resistance plus some RC. So that will give very high value of the resistance in the denominator. Then automatically current I is equal to V by RC plus R. Then the current is going to be limited. The series combination of resistor and capacitor in parallel with the SCR, we call it as a snubber circuit. That's all. So by make use of snubber circuit, we can prevent the dV by dt triggering. This is the explanation behind it. To prevent dV by dt triggering, we make use of a snubber circuit. What is the snubber circuit? Series combination of resistance and capacitor are connected in parallel with the device. That we call it as a snubber circuit. So now we'll see the gate triggering. So there is a gate triggering is very simple, reliable and efficient. Therefore, most of the firing schemes are in the laboratory or maybe any conventional methods to fire the device. We used only gate triggering. So that is what the method of firing the SCRs. Now why VBO is problem? We can see that VBO in the sense as a forward voltage triggering case, as a thyristor, VBO is let it be 800 volts. Some example. And then when the normal thyristor rating is 400 volts, let us assume that. If I don't want to give the gate signal, but I want to fire the device, what I have to do? I have to apply that voltage to up to 800 volts, then only the VBO will reach, then only thyristor will trigger. But is it safe? Because after all the device voltage, in this case working voltage is 400 we want to operate, but if you give 800 volts across the device, then automatically that process is already is a unwanted process. That's the reason generally we don't use that. That is the reason remain in the forward blocking condition until if you make that voltage is under 800 volts. If you give only 400 volts, the device is a off state only. Now with gate current established, charges are injected into the P layer because of either two things here. One thing remember, either you can pass the gate current or you can pass the voltage across gate and cathode, not from anode to cathode. There is a voltage across gate and cathode also you can apply. Then we can see that current pass through that is going to be minimum. Once that IG minimum reaches, that is a minimum gate current is required to trigger the SCR. IG maximum is a maximum gate current it can allowable. So while you are giving the gate current, it should not be beyond that. So within a limits you have to provide the gate current either minimum or below maximum. That way. So now the forward voltage at which device switch to on state depends upon the magnitude of the gate current. Like in the previous, I already mentioned, normal triggering voltage is a VBO, but if we increase the gate current, then the breakover voltage is going to be drops down. That I already shown you in the previous one of the slide. There is IG1, IG2, IG3 and so on. IG0. IG0 is without applying gate current. IG1 is some gate current we applied. Then the breakover voltage will be dropped down. If we further increase the IG2, I mean increasing the gate current, again breakover voltage drop down. Like that, if we keep on increasing the gate current, more electrons reaches to the junction J2, it is going to be breaks down with the less time, that is a less voltage across anode and cathode. So like that we are going to trigger, but how long I can increase the gate current, that should not be beyond the maximum. And while if you have, let assume that gate minimum gate current is 1 milliampere, but if you pass gate current is 0.5 milliampere, whether the thyristor will trigger or not, what will happen? Thyristor will not trigger because minimum gate current is required to fire the device. Even though if we give the gate current less than the minimum, but what is the breakover voltage required? We need up to VBO only. Breakover voltage, whatever the device VBO is there, that much voltage is required to trigger the device. Otherwise, device will not trigger, and that is the process. Then higher the gate current, lower the forward breakover voltage, and which positive gate current is applied at P layer, that is flooded with the electrons from the cathode. That's what all the electrons will reach. More electrons will reach when you give the more current, then it will be breaks down with the lesser voltage. So I will show that in the case of diagram also, then what is the relation and all, because these are all the internal process. As thyristor is forward bias, some of these electrons reaches junction J2, because already J1 as well as J3s are already, for whatever method we are following, we need to use only to break the junction J2 only. Whenever it is a forward bias condition, to break the junction J2 only, we need to apply all these methods. But some of the methods are not preferable, some of the methods are unwanted triggerings, but only this gate triggering is a preferable one. So now we can see that magnitude of the gate current is increased, more electrons will reach the junction J2. Therefore, thyristor will get turn on at much lower voltage applied across the anode to cathode voltage. That's what the logic. You can see here, this one. There is a relation. See the breakover voltage means what we call it as this line, I call it as a VBO, and further this is going to be decreases gradually. What is meaning in that? X-axis is a gate current. So if I pass the gate current, suppose somewhere here this value, this much value, if I pass the gate current is this much, then what is the breakover voltage? VBO only. Why it is VBO? Or up to OA. What is the breakover voltage? VBO only. What is meaning in that? Why? If I am increasing the gate current, breakover voltage remains VBO from 0 to OA, because 0 to OA is a minimum gate current is required to trigger the device, below which breakover voltage remains VBO only. Now from that point onwards, OA onwards, if I increase OA to OIG1, then what will happen? You can see I am increasing the current from this point to this point. Then this we can get it voltage across the device, means breakover voltage is this much. Earlier VBO up to here, previous one if it is OA, this will be breakover voltage. Now further increase the gate current, then what will happen? Breakover voltage is this much, and if you further increase this, breakover voltage is this much, and so on and so forth. We can see that whenever gate current increases, breakover voltage is going to decreases according to this plot. Now similarly, same thing you can notice here. Ig is 0. Ig is equal to 0. What is meaning in that? Gate current is 0. Means gate terminal is open. We need to apply only forward voltage anode to cathode. Once the voltage is reaches to VBO, device is going to be triggered. With that, we'll get VBO is this much. Now later what I did, I increased the gate current from 0 to something 1 milliampere or something like that. Then what will happen? Automatically breaker voltage reaches to V1. When compared to VBO, this V1 is less. Then further I increase the gate current from Ig1 to Ig2. Then breaker voltage is V2. Then this magnitude is less when compared to the V1, and so on. You can see that I am increasing the gate current further and further. Breaker voltage will be gradually decreases. So this way we can able to fire the gate triggering. So now you can see another one. There is a two transistor model of a SCR. So what is the two transistor model? As I said in the introduction class, that's why whatever topic we are going to cover from now onwards, all the topics must be already covered in the previous introduction classes. I mentioned this two transistor model in introduction. Directly, instead of using direct SCR structure, what we can do is we make use of two transistor. One is a NPN transistor and PNP transistor. We can able to get as a SCR operation. So that's why true transistor model or NPN and PNP transistors combinedly you have to connect such a way that it must be operate as a SCR fashion or a thyristor fashion. Now for that, what we need is we have to take it as normal structure of SCR, that is a PN structure, and bisect the middle layers and divide two parts. So once if I divide two parts, it will become as a PNP and NPN transistor. That's what you can see step by step. This two transistor model is obtained by bisecting the two middle layers. What are the middle layers? Normally we have P, N, P, N. These are the layers. So now what we'll do is we will bisect the middle layers. These two are middle layers. Once if we bisect this like this, if I bisect like this, what will happen? There is a PNP, then NP. This is the P. So there is another one is a NPN. So two devices will form. So what we will do is, there is a SCR 4 layers, you take it and bisect the two middle layers, that will become as a PNP and NPN. So that the connection, we'll see how we can able to connect that. So you can see this. This is the normal thyristor representation: anode, cathode, gate. There is an anode. We can see that P terminal, cathode is N terminal, gate is near to the P2 terminal. And as usual, there is a three junctions: J1, J2, J3. Now you need to bisect the middle layers. So what are the middle layers? These two are the middle layers. Bisect and separate it. If you separate, what will happen? PNP is a one structure, NPN is a other structure. So now you can see that after dividing this, what will happen? PNP 1 and NPN is a other structure. Now there is a anode and cathode and gate terminal. So this is the division of the device. Now PNP, you know the transistor, you can represent the PNP and NPN two transistor, connect like this, then we'll see what is your operation. The relation between the collector current and emitter current we can represent like this. Whatever PNP and NPN transistors are there, you connect like this. What is the connection here? You can see that base of the transistor 1 is connected to the collector of the transistor 2. This is the connection representation of the two transistors. You must connect like this, then only it will operate as a SCR. Base of the transistor 1 is connected collector of the transistor 2. Similarly, base of the transistor 2 is connected to collector of the transistor 1. And we can notice the anode current. What is anode current here? This is equal to gate current plus cathode current. So this is the anode current. You take sum of these two, we'll get it as a that current. Now you can see that cathode current, gate current plus anode current. So like this, we can get it as a these two relations. And now we can see off state of a transistor. Collector current is related to the emitter current. That simple expression. Collector current is directly proportional to the emitter current, or IC is equal to alpha into IE plus ICBO, where ICBO is a leakage current. So these leakage currents are very small. So you can neglect also in the relation or a formula case. Now we can see that where alpha is common base forward current gain, and ICBO is a leakage current, but that you can neglect. Let transistor 1, it is a general expression. If I consider as a transistor 1, then what I can represent, this is a IC1 is equal to, for transistor 1 gain I call it as alpha 1, and the leakage current I call it as a ICB01. And there is a emitter current. You can see here in the transistor 1, what is the emitter current? This is nothing but a anode current only, because this is a emitter current. This is equal to the anode current. So now you can represent the T1. IC is nothing but IC1 for transistor 1. Alpha is become as alpha 1. IE is emitter current. In our case, for transistor 1, emitter current is equal to as a anode current. Another one, this is ICB0. We can represent ICB01. That is for transistor 1. Similarly, for transistor 2, what we can represent? IC2. There is alpha 2. Then IE. What is IE in the case of transistor 2? Now we can see here. This one is a IE2. IE become IE2 for transistor 2. That is equal to sum of these two. You can add that. Then I can represent, you can see that there is a IC2 is equal to alpha 2, then IE is nothing but a cathode current plus leakage current. So now what is the cathode current also, you can replace it. So ICB02. And total anode current, because it is coming from anode, then we can represent two transistor model can be current IA, IC1 plus IC2 based on our circuit KCL. Now there is IA alpha 1 into IA plus ICB01 plus alpha 2 into IK, because that is the transistor 2 model, and you just simplify by gate current, something IG is a gate current. So you can simplify that IK as per our diagram. You can see that there is a transistor, this is a IK, where this is coming, IK is nothing but IE only, but if we combine this structure, it is coming from anode current. So anode current plus gate current will give as a IK. Therefore IK is equal to, you can write IG plus IA. So that will give as a IK current. That you can replace there. So once if I use this IK is this one, what will happen? In terms of IA will get it. So then IA is equal to, this is the expression. So final expression for IA is nothing but a alpha 2 IG plus leakage currents by 1 minus alpha 1 plus alpha 2. But these two parameters are negligible. Then alpha 2 IG by 1 minus this. Then what is this anode current? Anode current must reaches to the latching current, then only device will trigger. So how anode current is going to increase? How will increase? By increasing the alpha 1 and alpha 2. If alpha 1 and alpha 2 is increasing, 1 minus of that, the denominator will decrease, then anode current will increase. Once anode current increases, automatically keep on alpha 1 and alpha 2 increases. Once alpha 1 plus alpha 2 approaches to unity, then the SCR is going to be trigger. That is the reason We can see that, then we'll see how the alpha 1 and alpha 2 is going to be unity. Now there is a, we'll see start procedure, we can increase the alpha 1 and alpha 2. Anode is positive with respect to cathode, then Ig is 0 at that moment. I call it as a forward blacking state. This statement is fine, everyone. Anode and cathode is under forward bias condition until unless if we give gate or something else method, it cannot be triggered. So that is the reason we can see that it is, we call it as a forward blacking state. Now under this transistor 1 and transistor 2, there is a junction J2 is going to be present. So our intention to break the junction J2, and for that, as you know the formula also, Ia is equal to alpha 2 Ig something, this you can neglect, by 1 minus alpha 1 and alpha 2. You can see that alpha 1 is related to the transistor 1, and how this will be increases the alpha 1. If emitter current increases, automatically alpha 1 will increase. Similarly, this emitter current is increases, alpha 2 is going to be increases. That is the relations alpha and emitter. Now we can see that how alpha 1 plus alpha 2 is going to increase. The first stage, the gate current is applied, that is it act as a base current of a transistor 2. If I give some gate current here, then what is that? It is nothing but a base of a transistor 2. Is it fine? Simply we applied some current, that is a gate current, that is nothing but a base of a transistor 2. Once if we give base to the transistor, what will happen? We know that transistor will fire, means it will trigger. Once transistor is triggered, then what will happen? Collector current also will be increases. Once collector current increases here, if this is on, collector current will increase. That is nothing but a base of a transistor 1. The base of transistor 1 increases, again emitter current will increase here. So emitter current increases, alpha 1 increases, like this with the cumulative process. These are the sum of the relation. Collector current is equal to, because IC2, first this will trigger, no? That is a beta 2 related to transistor 2, that is a common emitter forward current gain, and into IB2. So now IC2 is nothing but base current of a transistor 1. That's what, whatever sequence I told, that only I represented here. So now this also will increase. Once if that is increases, IC2 is nothing but a beta 1 into IB1. IB1 is nothing but the same as this, because IB1 is equal to IC2 only. Then we'll get beta 1 into beta 2 into IG. And now what is further? This is what why the emitter is current increases, alpha is going to be increases. So keep on, if we increase the emitter current, automatically emitter 1 increases, alpha 1 increases, emitter 2 increases, alpha 2 increases, like that cumulative process. Finally alpha 1 and alpha 2 is approaches to the unity. Once if we increases the alpha 1 and alpha 2, automatically gate current, we started only the initial moment only. Gate current will not keep on changing. Initially gate current changes from 0 to 1 milliamperes of current. The base current of transistor 2 increases. Similarly collector current will increase, that will be the base of the transistor 2. Then emitter current will increase, like this continuous process. There is a alpha 1 and alpha 2 further increases with this reason. Then finally what will get it? Alpha 1 and alpha 2 cumulative or regenerative action is going to be takes place, and it towards in the unity level, and the device is going to be triggered. That is the method, gate triggering method of a true transistor model. Very simple logic, you can recall once. Gate current increases from 0 to 1 milliampere, the transistor 2 base will increase. Base current is given to the transistor 2, then the transistor 2 will trigger, that will be the collector current will increase, that is a base of transistor 1, that will be emitter current will increase, then alpha 1 will increase, like this cumulative process. Alpha 1 increases, again alpha 2 will increase, because Ik is equal to Ia plus Ig. If Ig increases, Ik will increase, that emitter current of transistor 2 also will increase. With this process, finally the device is going to be triggered. And similarly, the rest of the things are same as thyristor model only, no difference. The forward anode to cathode voltage increases, then across this structure, you can see the diagram if you recall. Inside all the two transistor model will be there, but there is a anode, there is a cathode, and somewhere there is a gate. Now if you apply voltage like this, anode to cathode voltage, then what will happen? Collector to emitter voltage of the both transistors will increase. There is a transistor 1 and transistor 2. These two will be coupled, no? So once across the anode and cathode, if you give the voltage, then what will happen? Collector to emitter voltage of the both transistor is going to be increases. That results leakage current at the middle junction. I shown no, there is in between, there is a junction J2 will be there. So leakage currents of the transistor Q2 as well as Q1 is going to be increases. With increase in the collector currents, IC1 as well as the IC2, that will cause the alpha 1 alpha 2 is approaches to unity, that is going to be fire the device. And similarly dV by dt, again same logic. Once the voltage applied across that will be higher, then the junction J2 will act as a capacitance. Then the rate, once the voltage is given suddenly from off state instant, the rate of change of voltage will be increases, and then junction J2 is going to be breaks down. And that is the mention same as current I is equal to Cj into dV by dt, and Cj is constant and dV by dt is proportional to the current. If it increases beyond the specified value, current also will increase, and then automatically junction J2 is going to be breaks down. And then we can see the rate of rise of anode voltage is large, then the emitter current will be large, and result alpha 1 plus alpha 2 will approaches to unity. That leads to the switching action. So same logic. And now temperature triggering. So at a higher temperature, forward leakage current across junction J2 is going to be increases or rises, and the leakage current serves as the collector junction current of the component transistor Q1 and Q2. Same temperature rises means again junction J2 temperature rises, again leakage currents will increases, that leads to the alpha 1 and alpha 2 will increase, again finally junction J2 is going to be breaks down. Same logic. See that IC1 and IC2 leads to increase, then alpha 1 and alpha 2 will increase, then finally it takes place as a triggering. But this is unwanted, again we have to make use of a heat sinks. So then light triggering. Light triggering, when the light is thrown onto silicon, that is a junction J2, electron hole pair will be increases. In the forward bias thyristor, leakage current across junction J2 increases, which eventually increase the alpha 1 plus alpha 2, same as in the previous temperature triggering concept. And then gate triggering is the most finally from this any method, whether you can use directly thyristor or you can use two transistor model. Gate triggering is the most common method for turning on a thyristor. So light triggering thyristors are used in the HVDC applications. So this is the today's class. The next class we'll see the dynamic characteristics of a SCR. So far what we observed is a static characteristics of a SCR. So in the VI characteristics, or you can say that. In the second case, what we'll do is a dynamic character. Dynamic characteristics means that from on state to off state what will happen, or off state to on state, both will see that. Initially it is in the off state, and now we need to make it as a on. Once if it is on, what is the process between off to on? Once it is already on, then what next? How to turn off the device. While the device is going to turn off, then what are the steps are involved? So all these things is going to be discussed in the previous class, that is a dynamic characteristics of a SCR. So once if you complete the dynamic characteristics concept, then we'll move on to the protection of a thyristor. So that's the dV by dt protection and di by dt protection. So all the why the protection, as we observed now in the previous explanation also, dV by dt, Why the dV by dt is going to be unwanted? Because once switch is closed, rate of change of voltage will high, that leads the conduction. So to overcome the drawback, we need to use there is a snubber circuit. So we'll see the design of snubber circuit related to some problems also. Then the over voltage protection and over current protection. So that is all related to the protection. So then later on we'll move on to the series parallel operation. It is very simple unit only. So static characteristics, dynamic characteristics, protection, series parallel operation, and then we'll move on to the commutation circuit. So once commutation is over, that is the end of the unit. So like that, in each class, try to understand the things. If you have any doubt, you can raise at any point of time, and I will share that PPTs in the each class. You try to read once, and that will be very simple in this will be very useful subject. So if you have any doubt, you can raise, otherwise you can leave.